All right. So this is notes 2 for the second day. And it says, let's go to the numerical approach. This means constructing a table of values, evaluating the function, blah, 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 several s values near 0, or use the results to estimate the limit. Okay, so I have this function. And yes, I can look at a graph to see what happens. At the moment, I cannot plug in 0, do direct, that's called direct substitution, because if I do that, you get 0 divided by, and then look at this, 0 plus 1, the square root of 1 is 1, 1 minus 1 is 0. You get 0 over 0. If you get 0 over 0, that's called indeterminate form, and it definitely has a limit. If you get 0 over 0, write that down somewhere. If you get 0 over 0, it definitely has a limit. And I wouldn't even write 0 over 0 anywhere, guys, because 0 over 0 is technically not even a thing. Definitely has a limit. Definitely has a limit. Definitely, 100%. If you get 0 over 0, it has a limit. All right, so let's see. How are we going to do it? Chavez, how are we going to do this? I don't have a calculator. Well, there's something called Desmos. So let me see if I can go to Desmos. Let's go to Desmos. Where are you, Desmos? Oh, okay. You guys are going to have to help me out. So someone unmute yourself and tell me what the equation was. F of x equals, and I know that I had an x in the top.
Yes.
Okay. X over
the square root of x plus 1.
Square root. Hold on, I'm going to have to SQRT x plus 1, and then I have to scroll out, right? Of that?
Yes.
And then what do I put? Minus 1? Did I get that correct?
Yes.
Okay, so you can see there, guys, you can already see what the limit is graphically. I don't want to pay attention to the graph. I want to pay attention to a table. So yes, I know what the graph it looks like, guys. But look, check it out. Look how awesome this is. I can just type in table. Oh, that sucks. Okay, add table. By the way, you should be able to type in table and it should work, but that's fine. Maybe because I have it in this mode. I take out the x1, I call it x, and I go to the y1 and I call it f of x. So just put f, and I need my little parenthesis, x, and then close it. And now I can just type in numbers. So what is the first value that I have on the table going left to right? It was a negative something. Was it a negative 0.2?
Yes, negative 0.2.
Negative 0.2. So negative 0.2, and there it is. There's my, so someone type that number in your table, and then you guys are going to give it to me when I go back. Give me at least 4 digits after the decimal. You can round or truncate it, doesn't matter. So write 1.8944. And then what was the next x value? Was it negative 0.1?
Yes.
Okay. Enter. And then write 1.9486, or you can even write 87 if you want. What was the next number after this?
Negative 0.01.
Negative 0.01. So here's what's happening. I'm getting closer and closer to 0 from the left-hand side. Enter. And write 1.9949. That's truncated. It would be 1.995 if you round it. But put 4 digits, so put 9949. And what's the next? Is there another one? Is it a 0.001?
Yes, it's 0.001.
Negative 0.001. And look at that. Write 1.9994 or 5. It doesn't matter. Okay, did we get all those numbers?
Yes.
Okay, awesome. All right, and then it's just, you should see a pattern. So does it look like I'm approaching something from the left? If I approach 0 from the left, and how do you know it's from the left? Because the numbers are negative. So if I approach 0 from the left, do you see the y values converging to a specific number?
2.
Yeah, it looks like it's converging at 2. And you can see that also, by the way. Look, you can see it also right here with the graph that I'm zooming in. And the graph is there. It shouldn't be there, but that's fine. All right, let's continue with the let's continue with the positive numbers now. So now I'm going to approach 0 from the right. I'm assuming that I did 0.2, 0.1, 0.01, 0.001. Did I do it that way?
Yes.
Okay. So let's do 0.2, enter, and write down that number, 2.095. And I know that you can already see what's happening, but just write down that number, guys. 0.1, enter. 0.01, enter. 0.001, enter. So write down those numbers, guys, and let me delete the others. That's fine. I can leave them there. Okay, so you can already see what's happening. So I'm going to go back to my notes, and you guys are going to tell me my notes. Come on, buddy. Share. Okay, so can you hook me up with the top table here? This was
8944,
1.8944, and then this was 1.9486,
486,
and then this was 1.9949,
49.
and then this was 1.9994. Truncated? Okay. And then this one down here was what again?
2.0954,
954, and then
0488,
2.0488, and then 2.049,
0049.
and then 2.0004. Okay. All right. So here's what we're supposed to look at with the notes. So this table here, it says let's approach 0 from left, getting closer and closer. So that's what we're doing. We're approaching 0 from the left, -0.2, -0.1, -0.01, -0.001. And as you can see, we're getting closer and closer to 1.89, 1.94, 1.99, 1.999. It looks like it's approaching 2. And then it says, now let's approach 0 from the right, getting closer and closer. So maybe you're probably used to having a table with x values increasing in value. But remember, this is not a normal table. All we're doing is getting closer and closer to 0. So 0.2, 0.1, 0.01, 0.001. If I wanted another one, I would say 0.0001. Because I'm getting closer and closer to 0, but from the right side. Does that make sense to you guys?
Yes.
Perfect. So we're getting closer and closer to 0 from the right side. So now it says this. So from this, we can conclude that limit as x approaches 0. Okay, well, am I approaching the same number from both directions? Well, you saw the graph. Yes, you are. But pretend the graph was not there. Just look at the table. Yes, you are approaching 2 from the left. You're approaching 2 from the right. So yes, we're approaching 2. And there it is. That's it. Was that cool or what? All right. I think that's really cool. So now we're going to let you guys give me these numbers. Make sure it's in radian mode. So someone go to Desmos.com, anyone, it doesn't matter who it is. Go to Desmos.com and then type in f of x. So what did we do? We did f of x equals sine x over x. Put that on the first table, and in the second table, you're gonna put insert the plus button, insert table, and you're gonna go x and f of x. So I would prefer more than one of you, but at least one of you do that. Yay, Shreya. And then help out Shreya with the numbers, guys, because you guys can see the notes and she can't. Obviously, we're approaching 0 from the left first. So what's the first number on the table?
-0.1, JK2.
-0.2, okay, 0.2. And then write the first 4 digits, guys. And then the next one I'm assuming was -0.1. And then write 0.9983. And then write -0.01, -0.01. 0.999, and then one more, -0.001. And then put 0.99999. And just for kicks, Treya, or Ms. Deenan, sorry, put in 0 on the next one. Just put 0 and see what happens. Look at that, guys. If you put in 0, why is it undefined? You can't tell on that graph. It looks like it goes right through the y-axis, but it does not have a y-intercept. It actually has a hole. Put that in your notes. Hole on the y-axis. Hole at 0, 1. Put that in your notes somewhere. That graph has a hole. You can't tell from the graph, but it has a hole there. All right, guys, now let's go from positive, from the right side, closer to 0. So all you got to do is erase the negatives, Ms. Deenan. Why did the values not change? Because this is an even function. So that's why the y values did not change. And you can tell that real quick just by looking at the graph that it's an even function. So go ahead and put those numbers in your table. All right, thank you, Ms. Dean. Someone hook me up. What were the numbers again? At negative 0.2, it was
9933.
0.9933, and then negative 0.1, it was 0.9983,
83.
and then negative 0.01, 0.99. Was it 9 again?
Mm-hmm.
And then what was the last digit?
9.
Oh, it was already all four nines?
Yeah.
Oh man, I should have done one more then. Okay, no big deal. Yeah, so I didn't know the fourth digit was already a 9. If not, we should have written 5. That way you can see. That's fine. That's fine. Okay, so from
Wait.
this,
You said they were the same because it's an even function?
yes, it's an even function. So that means that if you fold it right on the y-axis, the lines would overlap. Does that make sense?
Yeah.
All right, so from this we can conclude that the limit of sine x divided by x is, well, let's see, if I approach 0 from the left, what number does it look like I'm converging at?
1.
1. By the way, how would I write that? Like this: limit as x approaches 0 from the left of sine x over x equals 1. If I approach 0 from the right, how would I write that? Limit as x approaches 0, put the little plus symbol, of sine x over x. Since I already identified this as f of x, you probably, oh no, I didn't. Okay, this you'd have to write sine x over x equals 1. Because the left and the right match, do they match, guys?
Yes.
Yeah, they match. Because the left and the right match, you can say limit as x approaches 0 of sine x over x equals 1. Cool or not cool?
Is there a way to tell if it's an even function, like without without graphing it?
I guess if you know properties of sine x and you know properties of x, but there is, I mean, if it's something like, if I were to tell you y equals x squared without graphing it, x squared is always even. I guess here's what I'm trying to say. This is the properties of an even function. So if I type in a negative value, so yeah, there is. So if I were to tell you y equals sine x over x, if I tell you, is this even or odd, here's how you tell if it's even or odd. If I go y equals sine of negative x divided by negative x, well, notice, remember your properties from Precalc, sine of negative x is equal to negative sine of x. That's just a property from Precalc, right? Sine of pi over 6 is a half, and sine of negative pi over 6 is a negative half. And then, so that negative x there, so look what happens if I do that substitution. Negative sine x over negative x. Look, these negatives cancel out. Sine x over x. And look at that. So what does that mean? This means that f of negative x equals f of x. Hence, even. Good question, miss. So yes, there is. You can type in a negative x and see if you get the same expression. If you get the same expression, it's an even function. Okay, sorry guys, I took a good sip of my coffee here. All right, guys. So now that we know that, I'm going to erase this real quick. I want to talk about something. Let's see how smart you guys are. Don't type it into Desmos. I'm thinking you guys are going to get it correct. I hope it's for the right reasons. What do you think this is? Limit as x approaches 0 of x over sine x. What did I just do? All I did was what? There's a special word for it. It starts with the letter R.
The reciprocal.
Yeah, the reciprocal. What's the reciprocal of 1?
1.
Yeah, it's 1. So both of these properties are true, guys. These are the big ones. This one's the big one, really. Limit as x approaches 0 of sine x over x. Only as x approaches 0 will this be 1. All right, without graphing, let's see. I want to see how good we are, guys. Without graphing, what do you think this limit is? Let's think about it. Don't graph it. Just what do you think that limit is? Take a guess. It's okay if we're wrong. All right, I'm going to explain it to you guys, and then hopefully you guys can take a guess to see what's happening. Sine x, do you guys agree that all sine x does is just a little wave? It's just a wave going up and down like that. Do you guys agree?
Yes.
Okay, look what's happening. X is approaching larger and larger and larger. So you have a little wave where the output is somewhere between -1 and 1. And you keep dividing by a bigger and bigger and bigger number. What's going to happen to the output?
It's getting smaller, question
Yeah.
mark?
It's getting smaller. You're converging on a specific number, though. So we're not getting smaller forever and ever and ever. Well, I mean, I guess technically you are. You are getting smaller forever and ever and ever. But you're converging to a specific number. What number is that?
0.
It's 0, perfect. Because in math, -10 is considered to be smaller than 0. I know it's ridiculous because in physics, that's not smaller, it's magnitude more. But in math, the more negative you are, the smaller you are. Yes, you're converging to 0, guys. So be careful. If x is approaching infinity for sine x over x, you're converging to 0, period. And of course, the same rules apply for, I'm getting ahead of myself. I don't want to talk about horizontal and vertical just yet. But we'll talk about that hopefully this week. All right, let's go to the next page. Here are the special limits. And relax, guys. This one, number 1, is the one that you will be using the most. This one comes out, not often, but it comes out. And this one, number 3, it does come out often, but it comes out more often when we start talking about transcendentals, when we start talking about E and what it means to be an E. So we're going to save those for later on, but number 1, we're going to use all the time. Cool? All right. So look at theorem 2. It looks hard. Relax. It's not even that bad, guys. For real, trust me. It looks hard. You're like, what the heck is all this? This just means polynomial. It's a polynomial function. That's all it means. And n can be any power. So if this were to be the power 3, this says n minus 1, that's power 2. And then it keeps going on to you just have just a number. See, so don't worry. It's just like, it's nothing hard. It just means polynomial. And what this says, if f of x and g of x are polynomials and c is any real number, then what this is saying is you can do direct substitution as long as you do not get a 0 in the denominator. Well, we already knew that. I think we already knew that. I think we kind of talked about this yesterday. We already knew that. So for example, if I have a line, x plus 3, well, we know x plus 3 looks like this, where this is 3. If I tell you what's the limit as x approaches 1 of x plus 3, well, yeah, if I'm approaching 1, this is all real numbers, my domain. If I'm approaching 1, what am I converging at? Well, that has to be 4. It has to be. Because the line x plus 3, when x is 1, the y value is 4. Does that make sense, guys? Say yes or no, because I can't hear you guys.
Yes.
Yeah, perfect. That's all we're doing. So if you have a fraction, and as long as you don't get a 0 in the denominator, if you can do direct substitution, do direct substitution. That's all it means. That's all this means. So that's the beautiful part about this, guys. So see, look, easy stuff. Nothing crazy.
Wait, Charles, I'm confused.
Okay, ask.
You substitute what into what?
Whatever the x value is into the expression that they want us to find the limit of. Does that make sense?
Yeah.
So look at this letter A. Look at example 3 here. It says the limit of x squared times 2 minus x when x is approaching 3. Well, it's not a fraction. I can just do direct substitution. As soon as you do direct substitution, you do not need to write the word limit anymore. 3 squared, 2 minus 3. You don't have to write the word limit anymore because we're already evaluating it. Excuse me. 3 squared is 9. 2 minus 3 is negative 1. So you get negative 9. Cool, guys? Cool.
Wait, so you can only directly substitute when it's not a fraction?
No, you can do direct substitution in the fraction as well. You can only not do direct substitution if you get a 0 in the denominator.
Oh,
Because remember that if you have a 0 in the denominator, you're undefined. Does that make sense?
yes.
Now, if you get 0 over 0, that's indeterminate form, and you're gonna have to do something else, either with a graph, with a table, or algebra. Don't worry, we're gonna do some of those. We're getting ahead of ourselves a little bit, I think. All right, here we go. X squared plus 2x plus 4 over x plus 2. I can do direct substitution because I do not get a 0 on the bottom. So here we go. I do not write the word limit. I just go 2 squared plus 2 times 2 plus 4 over 2 plus 2. Let's see what that is. 2 squared is 4. 2 times 2 is 4. Plus another 4 all over 4. So 4, 8, 12 divided by 4. That's 3. I guess you didn't have to do that. You can say how many 4s are in the top. There's 3 of them. So 3 fourths. So there it is. Cool or not cool? Cool. Okay, that was me talking on your behalf. All right, here we go. So here's your answering the question that someone just asked. We can't do direct substitution, so we must use a property that we learned earlier. So why can I do, real quick, why can I not do direct substitution? Because if I try to do direct substitution, tan x over x, look at this, tan of 0, here comes your pre-cal, tan of 0 is 0. And as x approaches 0, well, that's 0. You can't leave it like that, guys. 0. If you have 0 over 0, it definitely has a limit. So you see this, and you're immediately thinking, did I write it up here? Oh, 0 over 0 definitely has a limit. Okay, the only property we know right now is this property. Limit as x approaches 0 of sine x over x. That's the only one we know, and that limit is 0. So what I want to get tan x over x to be sine x over x. Yes. So now we get to do our pre-cal, and we're like, yes, I'm glad I took pre-cal with Chavez. So here we go, guys. What is tan x? I'm going to put it here on the side what tan x is. Tan x in terms of sine and cosine. What is tan x in terms of sine and cosine? Oh,
Sine over cosine.
yes. All right, Godinez. The next question, you're not allowed to answer. I'm not saying that I don't want you to. It's just that we need someone else to answer the next one. So the next one, guys, it can't be Godinez. It has to be someone else. So maybe we'll just start picking random persons. So you know what? Like the next one's Mazuka. So get ready, Mazuka. You're the next.
Okay.
All right. Don't worry, guys. No pressure. No one judges here. Trust me. No one's judging. Guys, don't judge anyone. Because I'm not judging you guys, and no one should judge anyone. All right. So here we go. I'm going to rewrite tan x as sine x over cosine x, guys. Limit as x approaches 0. Sine x over cosine x. And I guess to be correct 100%, I'm going to write over x. Now, okay, I'm going to give you an easy question, Mazuka. So don't worry. It's okay if you get it wrong. Can I move that x right next to the cosine x right there? Can I do that, Mazuka?
Let me
What do you
think.
think?
Okay, so you're dividing by x. I think so.
Yeah, you can, guys. So side note, let's say I have a fraction AB and I'm dividing by C over D. So that's the same thing as saying AB, let me see if I can, that's the same thing as saying AB divided by C over D, which is the same thing as saying AB times D over C, which is AD over BC. All right, Chavez, what's the whole point of all this? Well, let's pretend that D is 1. Then it's like, see, it's like this fraction here. This A over B is like sine X over cosine X. And then look, that D was 1, right? So that's a 1 right here. And now that D goes away. So look, that B is like cosine X and the C was like X, and you just have them next to each other. Yay. So yes, you can just move that X up there like that. It's the same. So way to go, Mazuka. So next is, let's see. Is this giving you guys anxiety? I'm not trying to give you guys anxiety. Next is McManus. So here we go. I'm going to write the word limit because I haven't evaluated it yet as X approaches 0 of sine X over X cosine X. Is everyone okay with that statement? All right. I guess, McManus, are you okay with that statement? Yes or no?
Yes.
All right, there. You got an easy one. So now look what I see there, guys. I see sine X over X. So I'm gonna expand it. I'm not doing anything crazy. I'm gonna write limit as X approaches 0, and if you want, you can put a giant parenthesis to help you out. So this is my expression. I'm gonna write sine X over X times 1 over cosine X, and then close my parenthesis. I have not changed anything, guys. If I were to multiply this out, I would have this expression, sine X over X cosine X. Cool or not cool? I'm going to answer for you guys. I'm going to say that's cool. All right, now that I've done that, I can rewrite this expression now as this. I can say limit. This is what you can do with limits. As X approaches 0 of sine X over X times limit as X approaches 0 of 1 over cosine X. If you don't like that, yeah, I feel like we're 2 rookies right now. You're not going to like that. Okay, don't write that down because I feel we're rookies and we're not experienced enough. We haven't talked enough about properties. What you're going to write down is the same thing that we just wrote over there. Sine X over X times 1 over cosine X. All right, here we go. We're going to evaluate it just with our knowledge of what we know that sine X over X is. So here's what we're going to say. I know what this limit is right here. So I come back and I'm looking at it and I'm like, okay, what is the limit as X approaches 0 of sine X over X? So anyone can answer this one. You're okay, Godinez. You can answer this one now. What is the limit as X approaches 0 of sine X over X?
1.
1. Perfect. Thank you, guys. So now I can just write 1 times this multiplication symbol is this one right there. Why did I do that? Because now I can insert 0. I can do direct substitution for this right here. Here comes your pre-cal. What is cosine of 0? Oh man, that's a hard one.
1.
1. What's 1 times 1?
1.
1. There it is. 1. There it is. That's my limit, guys. So if you want, you can add this limit as one of the special limits. It's not necessarily a special limit because you can derive it, but here it is. Limit as X approaches 0 of tan X over X is 1. It also the same thing for X over tan X. Okay, the reciprocal of 1 is still 1. So you can put that as your special limit. You can put it in with these if you want. You can call it number 4. It's not necessarily a special limit because it can be derived from that one, from number 1, but you can put it in there with those. Okay, having said that, here we go. Last page. Oh no, we still got 2 pages. Sorry, guys. Maybe we'll cut this into 2 days if I feel that we're getting tired. But I think we can. Well, you guys answer. Besides Godinez, do you feel tired? Do you think we've done too much?
No.
Okay. Okay, good. Let's keep going, guys. So here we go. Example 5. I'm going to say first, you always see if you can do direct substitution. Can I do direct substitution? No. Look, if I do direct substitution, 1 squared is 1. 1 minus 1 is 0. I get a 0 on the top. 1 minus 1, I get a 0 on the bottom. If you get 0 over 0, it definitely has a limit. I feel like I'm a game show host. Like it definitely, okay, I'll stop. So here's what you're going to do. Well, Chavez, how do I find it? I'm going to graph it, and I'm going to approach 1 from the left and 1 from the right. Yes, that actually will work. But with this, you can just do algebra stuff, guys. You can just do algebra. So here we go. I'm going to write the limit, the word limit. Chavez, why are you writing the word limit? Because you have not evaluated it yet. So write the word limit, expand the top. So if you want, you can use parentheses so you can understand what expression it is that you want to find the limit. Expand x squared minus 1. That's just the difference of squares. X plus 1, x minus 1. All over x minus 1. What's going to cancel?
X minus 1.
Perfect. The x minus 1s cancel out. Now that I've canceled the x minus 1, now can I do direct substitution? Someone say yes.
Yes.
Yes. What's 1 plus 1?
2.
There it is. You're done. That's my limit. As soon as you are evaluating the limit, you do not have to write the word limit anymore. All right, let's go to the next one. Letter A. Letter A is exactly like example 5, which, matter of fact, I probably should not have put letter A in there because it's the exact. It's just a fraction. So let's see. We cannot do direct substitution because we get 0 over 0. So here we go. I'm going to write limit as x approaches 1. Why am I writing the word limit? Because we have not evaluated it yet. I put a parenthesis because I want the whole expression to be in that parenthesis. X minus 1 over x plus 1, x minus 1, close. And then from there, we're going to cancel the x minus 1s. You still have a 1 on the top, remember, because it's a fraction. So I have 1 over, and then 1 plus 1 is 2. So what is this limit? It's a half. Yay, we're winning, guys. All right, now we can go a little faster. Don't worry, we're going to keep the speed the same. We're just going to try to pick things up a little bit. So look at this. I'm going to write the word limit as x approaches 0. Again, you cannot do direct substitution because you get 0 over 0. So I see in the top, I have an x squared that I can factor out. And I see in the bottom, I have a 5x squared I can factor out. So I'm going to do that. So I'm going to factor out an x squared, open parenthesis, and I'm going to say, well, that means I'm going to have 3x plus 20. In the bottom, I'm going to factor out a 5x squared, close parenthesis, and I'm going to have, let's see, x squared minus 2. All right, now that I have that, and I guess you don't necessarily need a parenthesis, but I guess to keep the same habit, I'm going to put the parenthesis like that. All right, now that I have that, I'm going to cancel what I can. I have an x squared, I have an x squared, boom. Now I can do direct substitution. So I'm going to put equals. Because I'm just evaluating it, you don't need to put the word limit anymore. So let's see, I'm putting in a 0. So 3 times 0 is 0, plus 20 is 20, over, and then I guess 0 minus 2 is negative 2. Negative 2 times 5 is negative 10. I guess I didn't have to factor out the 5, guys. I could have left it in there, but I wanted to factor it out at the time. All right, 20 divided by negative 10 is a negative 2. There it is. So that's my limit. The limit of that expression is negative 2. OMG, letter C. I don't know if you guys remember this, but you guys actually had this exact question in Precalc. Okay, and let me tell you what you guys had in Precalc. In Precalc, do you guys remember this? You had that exact question with this expression, and it was this one. You had to do that. If you look at your notes, you'll find it. But don't worry, let's not look through your notes right now. All right, I cannot do direct substitution because if I do direct substitution, you get half minus half, which is 0 divided by 0. 0 over 0, it definitely has a limit. Okay, I'll stop doing that, guys. I don't know if you guys find that fun or if it's getting to you guys, so I'll stop. All right, so what I'm going to do, I'm going to find a common denominator because we know it definitely has a limit. So I'm going to be like, okay, in the numerator, I'm going to find a common denominator. So I'm going to multiply the right by 2 plus x over 2 plus x. I'm going to multiply the left by x over x, and then in a little bit, I'm going to move the x up. So I'll write the word limit because I haven't evaluated it yet. Limit as x approaches 0. And then I'm going to open a parenthesis because we're going to have a pretty big stuff there. And let's see, x times 1 is just x over, and I'm going to write x parenthesis 2 plus x. You can distribute it if you want. I'm not going to distribute it yet. Minus 1 times 2 plus x is 2 plus x over, okay, hold on. Oh, sorry, guys. That's a mistake. It's a small mistake. Don't worry. It's a small mistake. Instead of x over x, I should have multiplied by what over what?
2 over
2/2.
Yeah, 2 over 2. So it's a small mistake. Remove the x's and put a 2 over 2 over there. 2 and 2. You can distribute if you want, but I wouldn't. So here we go. So now multiply this one. We're good. Everything's 100% correct now. So 2 plus x over 2 parentheses 2 plus x. And all this is still divided by x here on the bottom. All right. I'm gonna distribute this. So I'm gonna pretend like I have a parenthesis there, and I'm gonna distribute it like that, so I can have one common denominator. So I'm gonna put an equal sign. I'm gonna write the word limit as x approaches 0, giant parenthesis, 2 minus 2. I'm distributing the negative, minus x over 2 parentheses 2 plus x. Close it, and I'm bringing up this x just like I did earlier. So now I have that. Do we have any questions so far, guys? Is that a no? I can't tell.
No.
Okay, so now we're gonna zero stuff out. Let's see. The 2's cancel out. Okay, I shouldn't say the word cancel. The 2's zero out. And now that you've zeroed out those 2's, can I cancel out the x's? What do you guys think? There's an x on the top, there's an x on the bottom. Can I cancel it out?
Yes.
Yeah, now we can. Boom, boom, they're out. You still have a -1 in the front though, so don't forget about that. So now I can do direct substitution. So -1 on the top over, I'm plugging in a 0 for x, and then 2 times 2 is 4. And there it is, guys. All right, you guys are gonna love this example here. In this one, you're gonna absolutely love it. Check it out. Put a parenthesis around the 2x. I should probably start doing that there. It's always sign of something. The 2x is your expression.
Question.
Oh, what's up?
What happened to the other x?
I did direct substitution. I plugged in a 0
Oh, okay.
because now we can. You know what I mean?
Yes.
Perfect. As soon as you get it to an expression that you can do direct substitution, you plug it in.
Got
it. Okay. All right, guys. So here we go. Letter D. It says sine of 2x over x. We can't do direct substitution. You get 0 over 0. Does it have a limit? It definitely does. The only property you know is this one. Sine or limit as x approaches 0. Well, really, it can be anything, but that's fine. Of x divided by x. This always equals 1. Correct? Correct. All right. I can have, and you know what? I'm going to keep the x there. I'm just going to x. You can have whatever you want in front of that. You know what? Chavez, what are you talking about? Oh, don't worry. The parentheses or the expression or it's called an argument. The argument, that's the way you officially call it, whatever's inside the parenthesis. Your argument must be the same. Like for this expression to be always true. Chavez, what are you talking about? Like this. Happy face. Happy face. As long as I have it looking like that, that property will be true. Now, if you don't like happy faces, you're like, Chavez, I don't like happy faces. I'm not a happy face person type of person. I like to have triangles when I'm talking about math. Like, all right, Debbie Downer, we'll put your triangles. We'll put your triangles. It has to look like this in order for this property to always work. It doesn't matter what. Cool or not cool? Someone say cool.
Cool.
Cool. All right. So now that I said that, we're going to play chemistry. What am I missing in the bottom for this to equal 1? A 2. Perfect. I'm glad you said it. It's just missing a 2. Now, if I do this, that's magic. I must balance it out. I have to. I just put a 2 in the bottom. In order for me to balance this out, what must I do to the top? I put a 2 in the bottom. That's magic. I need to balance it. I need it to be 1.
On the top.
Put a 2 on the top. So look, I'm gonna put the 2 right there. So now it looks like this. So let me show you how it really looks like. It looks limit as x approaches 0, and then I'll have, this is what it looks like. 2 sine 2x over 2x. Well, look, guys, look what you just did. This that I'm circling, sine of 2x over 2x, that is just what?
1.
That's just 1. And then I have a big giant 2 in the front, so that I have 2 times 1. And 2 times 1 is just what?
2.
Yeah, so there it is. And that's how easy it is. This limit is 2. Don't worry, we're going to practice a lot. We're going to practice a lot. We're just not going to just do 1 and that's it.
Wait,
All right.
child.
What's up?
Why is sine of 2x over 2x 1?
Oh, because of the happy face property.
Oh,
Sine
haha.
of happy face x over happy face x is always going to be 1.
Okay, I got it. Thank
You do not like happy faces, Godinez? No, I'm kidding.
I love happy faces.
I was joking, miss. I promise I was. Okay, here we go. Let's continue, guys. We're almost done. We only have 3 more. Ooh, letter G looks like it might be a killer. It looks like we might need some pre-cal on that one. Okay, so letter E. 5 cubed is 5 times 5, 25. If I have 5 quarters, that's $1.25. 125 minus 125 is 0. 5 minus 5 is 0. Oh, I get 0 over 0 again. Okay, since you get 0 over 0, I know I definitely have a limit. So I don't know if you remember, this looks like the difference of cubes. Do you remember from your algebra days what the difference of cubes formula looks like?
No.
If you're math life, you just know these things like in your brain embedded. Like it brings you joy. Like, hell yeah, I know the difference of cubes. The sum of cubes, let me write the sum of cubes as well. A cubed plus B cubed. Watch me be wrong. That would suck. A plus B, A squared minus AB plus B squared. We're right. All right, here we go. So I have the difference of cubes on the top. So here's how it's going to look. I write the word limit because I haven't evaluated it yet as x approaches 5. And I'm going to write giant parentheses because I'm going to have a whole bunch of stuff. And I put x minus 5, close, open, and then x squared plus, let's see, a, in case you want to know what a is and what b is, a is x and b is 5. So it says ab, so that means it's going to be plus 5x, plus, and it says b squared, so 5 times 5 is 25, over x minus 5. Now that I have a product in the top divided by a quotient or divided by something, I couldn't say divided by something, that was wrong statement. Now that I have a product in the top divided by another factor that's the same, those are going to cancel out. See? And now we can do direct substitution. So now I'm just going to say limit as x approaches 5 of the expression x cubed minus 125 over x minus 5 equals, and I can just use this guy right here just to plug in what 5 is. Let's see. 5 squared is 25, plus 5 times 5 is another 25, plus another 25. I have 3 25s, so it looks like that limit is just 75. And there it is, guys.
Wait, Tom, I thought you canceled out the x minus 5.
I did cancel. Oh, yeah, no, I did cancel them out. When I canceled out the x minus 5s, all I had left was this expression, and that expression's in the top.
Oh, okay, okay.
You know what I mean? All right, letter F. Don't freak out. You see a sine x, and you immediately write somewhere, limit of x approaches 0 of sine x over x is 1. Write it down somewhere, doesn't matter where. And then you're like, okay, well, I need to make this guy look like sine x over x. So let me put it in blue, guys, to differentiate from E. So I'm going to write, how am I going to write it? Limit as x approaches 0. And since I'm going to have some stuff being multiplied, I'm going to put a giant parenthesis. And I'm going to write, look what you can factor out on the bottom. You can factor out an x, 2x minus 1. Do you guys see that? So maybe you guys don't see it, so I'll write it again. X, 2x minus 1. And now look, I am circling this part right there. So now I'm going to expand it. I'm going to write limit. I'm expanding it, guys. As x approaches 0, giant parenthesis, and I'm going to write it like this. Sine x over x times, this 2x minus 1 is still on the bottom, 1 over 2x minus 1. So limit as x approaches 0. Actually, you know what? I don't even need the word limit anymore. I can just solve for it now. Sorry, guys. Equals, let's see if we can do this. Sine x over x. I meant to use green. Sine x over x. That is just 1 times. I can do direct substitution on this guy because I can plug in a 0 there. 2 times 0 is 0. 0 minus 1 is -1. 1 divided by -1 is
-1.
-1. Why did I put it in parentheses? Because I do not want it to look like 1 minus 1. Especially with the, I know with the dot you probably can get away with it, but put the parentheses in there, guys. So 1 times -1 is just -1. So there it is. That's my limit. This whole guy is just, you can rewrite it again if you want. Limit as x approaches 0, sine x over 2x squared minus x is equal to -1. And you're done. All right, letter G. Ooh, letter G. All right. Let's see. Let's see. What have we learned? All right, look at this one. Remember I told you guys to put that one as a special one? It's not really a special. It's not special because you can derive it from the sine x. You can derive it from this one. But put it down as a special one. So I'm going to talk about that one again. So I'm going to rewrite it over here. Just like the sine x over x, I'm going to write this. Limit as x approaches 0 of tan happy face x over happy face x equals 1. Always, always, always. You can also say the reciprocal as well. So put that as a side note. Side note. All right. You see 1 minus secant squared and you're thinking, Chavez, I have no idea. The only thing I know is sine x over x is 1 and tan x over x is 1. That's all you need to know. How do I turn this into a tan x? Well, okay, you know what? Refresher. So let's do that. Refresher. Worst case scenario, if you got this from Precalc, you're winning. Cosine squared theta plus sine squared theta equals 1. Now, hopefully everyone knows that. Your cosine squared, your significant other sine squared, and together you guys are 1. All right, the only way to get a secant squared, is 1 divided by cosine. That's the only way. So I'm going to divide that by cosine squared, divide that by cosine squared, divide that by cosine squared. So now, cosine squared divided by cosine squared, that's 1. Sine squared over cosine squared, that is tan squared. And then 1 over cosine, that is secant squared. See? And that says 1 minus. So in order for me to get a minus, I got to move that to the left, and I got to move that to the right. So look at this. 1 minus secant squared theta is equal to a negative tan squared theta. All right, that's all the refresher you need. So now I can rewrite. So I'm going to go and rewrite this limit. Don't worry, guys, we're almost done. This is probably about as hard as it gets. Limit as x approaches 0. 1 minus secant squared is the same as a negative tan squared, but I got to keep the argument in there. So I'm going to say negative tan squared, and I got to keep that 4x. 4x, because that's just the argument. Over, and if you want to expand this, you can, but I'm going to leave it as 6x with a square on it. Excuse me. All right. Now what I want to do is I want to use this. You know what? It's probably a good idea to expand it then. 6x times 6x is 36x. 36x squared, sorry. All right, here we go. Because I'm expanding it, I'm going to use parentheses. Limit as x approaches 0, giant parenthesis. I have a negative somewhere. And that says tan squared. So I'm going to write it like this. Tan of 4x over something times tan of 4x over something. Do you guys agree that that is still tan squared of 4x? Someone say yes.
Yeah.
Okay. And I still have, you see this 36x squared? That is an x squared. I can say x times x. So there it is. So I have already taken care of everything. The only thing that I have not taken care of is the 36. So I'm gonna write 1 over, and what do you think I'm gonna put here on the bottom?
36.
Yeah, 36. Travis, what are you doing? All I'm doing is plain balancing. That's all I'm doing, just like in chemistry. I'm just balancing, guys, that's all. Okay, I'm gonna take a different color. I need this guy, you know what? I'm gonna put this in parentheses, another parenthesis to isolate. I need something down here. I need something down there in order for me to use this property. What do I need?
4.
A 4. Now, this is magic. You can't just add a 4 in the bottom. If I put a 4 in the bottom, what do I do to the top?
Multiplied by 4.
Multiply by 4. So look, notice where I put my 4, so I wouldn't get confused. Same thing with the other one, guys. I'm going to put a 4. If I put a 4 in the bottom, then I put a 4 in the top. All I'm doing is chemistry, just chemistry. And there we go. We finally got our work. This expression, all of it is 1. Don't forget the negative. That negative, I'm going to put it right here. Times another 1 times, let's see, 4 times 4, that's 16, over 36. So there it is. And that looks like it reduces. So equals, let's see, negative 16 and 36 are both even. 8 over, what's 16 over 36 reduced to, guys?
4 over 9.
4 over 9. Perfect. 4 over 9. Why did that take longer than it should have? All right, there it is. And that limit is negative 4, 9.